Thanks everybody for coming. My name is Brian Payne. I work at Dropbox on traffic and performance engineering. Would like to talk to you today about how we built an edge network with NGINX to make our services faster for users on the other side of the world. Things started out simply enough for us. We built ourselves an online service, and people used it to store their content in the cloud, to sync data, and to collaborate. People used it a lot. We grew to hundreds of millions of users, exabyte scale amounts of storage, billions of files being synced every day by people all around the world. Undersea network cables carried the bits back and forth at nearly the speed of light, which sounds pretty good, except that light isn't actually all that fast. And the oceans are kind of wide. And when you look at the round trip times, it takes quite a while to get across the Atlantic and back, and even longer to get across the Pacific and back, which was a performance concern for us. We wanted things to be fast. Consider the experience of somebody who is in Asia trying to sync files with a server located in the US, say 150 millisecond round trip time away. The client first reaches out across the internet to introduce itself. Somewhere a server says hello in return. We want to do SSL to keep things secure. So we exchange SSL greetings. The server sends a certificate. The client and server then do a bunch of math to do a Diffie-Hellman ephemeral key exchange to ensure perfect forward secrecy. So far, so good. Finally, they do one last handshaking step, and we've got ourselves an Ssl connection. Great news. A computer has made friends with another computer. Nothing useful has happened at the application layer, however. And about half a second has elapsed already with the user waiting impatiently. You can cut out some of these round trips. It's pretty straightforward to do TLS false start, which will remove one of those 3 round trips. If you're feeling especially bold, you can do TCP fast open to cut out another round trip. But no matter how fast you do the handshaking, there's another problem that looms. TCP. TCP is a somewhat cautious protocol. When you fire up a new TCP connection and one side wants to start sending, it'll engage in slow start, sending out typically 1 or 2 packets, waiting to hear that they got across the ocean safely before allowing a slightly larger group to venture forth. Then, with each received ACK, it grows the current send window up at about 64K of cumulative data sent. It'll transition out of slow start and into whatever the chosen congestion control algorithm is, and gradually ramp its way up to the point where the send window size has reached the bandwidth delay product of the link. And at that point, and only at that point, you're sending at full speed. So eventually you get to be able to use the full link capacity, but it takes a while. Here's an actual Wireshark graph of what happens when going across an ocean trying to upload a file. The slow start hurts you, the chatty network protocol handshaking hurts you. We wanted things to be a little bit faster. We had already done some of the easy things. For static content, we were long since using a CDN. That meant that simple, straightforward things that every user requested, images, CSS, JavaScript, and the like, why those we could store close to the network edge and download pretty quickly. But the nature of our business involved a lot of dynamic traffic. People uploading their files to the cloud, syncing back to their devices. So we wanted to make the dynamic stuff as fast as we could also. On the server side, we had long since done the now common optimizations using a really large initial congestion window for TCP, picking our congestion control algorithms to try to be reasonably aggressive in the face of packet loss. And we had a reasonably well-tuned sending stack on the server side. That's only part of the problem solved, though, because the other half of our traffic is users uploading stuff. And when you're uploading stuff, you're at the mercy of the client's network stack. And wanting to support a diversity of users with different devices on different platforms and operating systems, we couldn't necessarily assume a highly tuned, modernized TCP stack. So we were kind of stuck. We couldn't necessarily rely on protocol optimizations client-side to decrease the number of network round trips. We could, though, take a shortcut by making those round trips shorter. We took some NGINX proxies, put them near the edge of the network, close to the client, thus inherently far from the data center where the data and applications lived. What does this do for us? Well, all of a sudden, if we're terminating TCP and SSL at the client, at the network edge, we're doing those chatty initial bits of the conversation, the ones that take 3 back and forth round trips. We're doing them over a much shorter RTT. Interestingly, if we've provisioned enough buffer space for that edge NGINX, we can also allow a client to upload quite a lot of data, get itself past TCP Slow Start, buffer the upload in RAM at the NGINX edge server without having to wait for a trip across the ocean back to the origin data center, which would take a long time. So we've got some advantages there in terms of, at least on the client side, not changing the protocol, not changing the number of round trips, but making things more efficient by making those round trips a whole lot quicker. But we're a proxy, and eventually we've got to get back to your data and your applications at an origin data center somewhere. And that's somewhere maybe a long, long way away, over a long round trip time, and all the performance considerations apply there too. We started out with a pretty straightforward configuration, setting up NGINX at our edge nodes to proxy, to servers, to VIPs at an origin data center. Note that we use HTTPS for the upstreams. Because we were terminating SSL at the edge, we wanted to keep our commitment to customers to keep their data safe, so we re-encrypt for the backhaul back to the origin. This is a good start, but we need to do some more things. Since we've got to go through the TCP and SSL handshaking in order to get one of these back-end connections up and running, we want to get as much mileage out of it as we can to amortize the cost of having set it up across a lot of subsequent requests. So we turn on Keep Alives. We also use HTTP 1.1 for the communication to the upstreams. Why 1.1? Because we were concerned about cases where either the client or a server application might be using 1.0 or 1.1 even, and terminating a message by closing the socket, which is valid in HTTP if you've not got a content length or chunked encoding, which if you tried to tunnel that over a 1.0 upstream, would have the side effect of tearing down this connection that we were trying to get a lot of reuse out of. So 1.1 and chunking on the upstreams proved to be pretty helpful for us. We also had to do some tuning on the operating system. Note I talked earlier about TCP Slow Start and how its conservatism made it kind of slow initially to get a connection up and running at full speed. TCP in general and Linux implementation specifically default to doing a thing that might have some benefits but is kind of bad in our situation, which is if a connection goes idle for long enough, the OS will drop it back into slow start mode. If you're keeping a connection pool of idle connections so that you'll always have one ready to use, by definition, you've got a handful of idle connections at any time just waiting for some work. You want those to be running at full speed and not drop back into slow start. So it's best to turn off that default feature. Here's how to do it in Linux. So at this point, we had things reasonably well tuned from a performance perspective. We needed to do some extra security work, though, to deliver on our promise to users that we would be keeping their data safe. We're already using SSL on the upstreams. That's a good starting point. But since we control the client, the proxy, and the server at the origin in this case, we can tune our SSL implementation to be a little bit more secure than we would if we had to accept any old client on the internet. Particularly, we can choose a modern TLS version. We can choose a cipher suite that we trust. We can choose a cipher suite with perfect forward security. Perfect forward secrecy, pardon me. These things you might not always be able to negotiate with a client connecting directly from the internet, but here we control client and server sides, so we get to pick the SSL configuration to be as hardened as we need it to be. This is a start, but there's some more we have to do. In NGINX, you can, and you should, configure your SSL upstreams to validate the certificate that the backend server is presenting to make sure that it's who you think it is. Here's how to do that. If you remember nothing else from this talk, please remember upstream SSL certificate validation. You can pin certificates with that penultimate line there to say, here are the certs or here are the roots that I trust. That's important because it helps defend you against somebody attempting a man-in-the-middle attack by getting a certificate for your domain name, intercepting the traffic, and pretending to be your upstream in order to steal traffic. This does require a relatively modern version of NGINX. This was added in NGINX open source 1.7. This alone is good reason to upgrade. So we had this idea, we'll have our proxy. It will communicate very quickly with the client because it's close to the client. It'll communicate quickly and securely with the server at the back end because of all the optimizations I talked about. So we wanted to find out empirically if it was any good. So we did some tests in Europe. We put some proxies in AWS in Europe, measured the upload and download speed for multi-megabyte block traffic, the sort of thing that is hard to accelerate. And what we found is, on average, we got about a 20–30%, some cases 40% speed up. Here you can see results at various percentiles of client speed, just by virtue of putting that extra proxy hop in the path. So a modest but significant performance speed up just from having an extra edge proxy in the picture. Recall, though, that we also wanted to make uploads fast. So we tested upload speed. Here found that we could get, at the median, a 20% improvement in how fast users could upload large volumes of data into our cloud from across the Atlantic just by having a well-configured proxy close to the user. Then we thought, those are okay results over a modest round-trip time. What if we tested across the Pacific where the RTT is much higher? And so we ran some trials in Asia. And there we found out that at the median with a proxy close to the user, we were able to get about a 70% speed up in large block downloads at the median. But we also wanted to make uploads faster. And so we tested uploads in Asia through this proxy. and they got twice as fast. And so with these results in hand, with this proof of concept successful, we've been pondering what are our next steps with this technology. Given the perf results were pretty good, especially for users far away from data centers, we elected to roll it out to all of our enterprise customers. And we've seen that the types of results we got in our trial in terms of percent speedups have been echoed in the results that real users are seeing. And so we're happy with that. Now my challenge for the next several quarters is to scale this up to handle all of our customers, enterprise plus consumer worldwide. Having an edge proxy that's NGINX, which is speaking HTTPS and is pretty configurable, also opens up the door to new interesting sorts of optimizations. If you've got multiple origin data centers and different apps are at different data centers, or different users' data is homed in different places, or you know that certain data is warm in the caches for a user in one location and not another, all of a sudden your edge proxy that happens to be a relatively flexible HTTPS server with some plug-in language APIs gives you a good place to put in some application level intelligence and say, oh, I recognize this user, perhaps based on a cookie or an SSL session. I know that I want to send this user to location A because that's where I'm most likely to have their data warm in cache. Or I can send them to location B if I know for capacity reasons that A is a bit overloaded at the moment. So all of a sudden we've got an opportunity to do a lot of things based on knowledge that the protocols don't have, but the application does. So what if you'd like to build your own edge termination acceleration network? Building out one of these at very large scale is a big investment. The way to do it with low marginal cost at multi-terabit levels of traffic involves building out your own POPs and colos around the world, doing your own networking deals to get peering and transit at reasonable prices. But if you're starting out small, or if you're just doing some testing to determine, will this help my application? Cloud hosting can help you out a lot. You got to figure out where in the world you might want to host. Chances are a lot of places where you might want to put nodes in your edge network are places that your favorite cloud providers also have a presence. Then you've got the challenge of, I've built out my edge proxies in locations around the world close to where my business's customers are. How do I get the right user to the right location in my edge network if I'm in lots of places? There are several ways to do this. The three that are common are use DNS with either latency awareness or geo awareness to send users to the location that's close to them, where close can be defined in terms of network latency or defined in terms of geographical proximity. A lot of people do that, a lot of CDNs do that. It works relatively well. Pardon me, another thing you can do is Anycast TCP. Some CDNs are starting to do that. Some companies are starting to do that for their own networks where they've built an edge presence. With that approach, you're letting BGP do the work for you in order to get the right users or the right subnetworks worth of users to preferably the ideal POPs. Versus DNS, there's a lot of trade-offs, and that's a whole other hour I could spend talking about the pros and cons and how to choose one versus the other. But there's momentum for both gaining a lot of adoptance. Finally, depending upon your application, you might be able to have the app itself make the decision. For example, if you've got some initial request that your client does to the application, that tends to be something relatively lightweight and perhaps not as performance sensitive, and you're sending them back in one form or another some links to tell them where to go next, by the time your application gets that request, that first request from the user, you know their IP address with great certainty. You can figure out where in the world they are. You can make an application layer decision about where do I want to send this person, and send them back HTML or JSON if it's feeding their app or what have you, containing links to the specific location in your edge network where you want to send them. And I've seen CDNs and companies with their own edge networks using combinations of these three techniques. Some techniques work well within a continent, but not so well across continents. Others work well for CDN traffic, but not for initial dynamic requests. Understanding your own business and your own usage patterns is key to figuring out what tools out of this toolbox to pick up and apply for a particular situation. And so if you want to try it yourself, our finding is that it can be done pretty easily and relatively cheaply. Put an NGINX proxy in place close to your users. Do the tuning for performance to make sure you get great mileage out of your backend keep alive connections. And finally, please, please, please make sure that you're using SSL on the upstream, and you're doing certificate validation and pinning in order to make sure that the content that you've told your user is secure stays secure in transit. Thank you very much. Questions? Yes, sir.
My question is, how do you guys handle, like, say, the European consumer Dropbox traveling in the US, accessing their files, as far as routing to their data?
Got it. So the question is a user who lives in one part of the world, traveling to another part of the world, wanting to access their files. We're currently making the decisions of what edge location to route to based not on who the user is, but based on where they are network-wise, which will get them to a POP that is close by some combination of geographically close and network RTT close. And from there, it becomes the POP's job to figure out within the edge proxy where's the right place to send them based on whatever we can figure out about where their data lives.
And I guess along that, do you guys have to adhere to, like, privacy laws in Europe in handling customer data across the US?
Yes. So the question was privacy laws in Europe and how that pertains to customer data in the US. Part of the answer involves US State Department safe harbor compliance. The long answer to that really turns into an answer to the question of where do you store data around the world. And that becomes a whole other talk that I couldn't attempt to answer in its due completeness in the time we've got. Yes? Yeah, so the question was replication between regions. We've got multiple origin regions. On the back end, we, as data is written, commit it to multiple regions that are geographically diverse. We, for the most part, tend to have very strict consistency requirements for what we do, which is good for this sort of service that we're providing, especially if users on a team that's distributed all across the world are collaborating on documents that are stored in one place and they all need to see an up-to-date view. That's good for us because it gives us good consistency properties. The downside for me as a person working on networking is that a lot of easy caching solutions aren't available to me because most of the easy approaches rely on eventual consistency. And so we've taken as a fundamental constraint that we've got to live with going back to data centers of record for certain types of requests. And that pivoted the question from how do we cache closer to the edge into, if we can't cache closer to the edge, how do we get you to the data center of record as fast as we possibly can? In the back, yes? Sorry, could you shout a bit? I can't hear from back. Sorry, I still cannot hear. Do we have a mic for the attendees?
My question was, once you terminated SSL at the edge,
Yes.
why continue to do HTTPS? Why drag along the HTTP stack within your data center?
So the question is, why, once we've terminated SSL at the edge, do we then re-encrypt to send over the long haul back to our origin data center? Because the world is full of threats. Sorry, I can't hear you from back there. Okay. So why HTTP instead of some other protocol? We looked at doing other protocols. We, in fact, did tests with custom UDP-based protocols that were more aggressive in their sending. What we found was that we could get comparable performance with HTTPS. And pragmatically speaking, as a small team within a relatively small company, we wanted to get as much mileage out of existing solutions as we could. And so we looked at it and said we could build a different transport layer or invent our own from edge back to origin. And we might even be able to get a couple of percentage points of extra speed from doing that. But in our tests, it was only a couple of extra percentage points. Conversely, if we stuck with software that we knew and protocols that we all knew how to debug, then we could use the same building blocks everywhere and get a lot more leverage, not just out of the code, but out of ourselves and our own time and experience. Yes? We considered IPsec. We thought about it. We opted for encrypting at application layer, in part due to that same consideration of, since we're going to have to implement HTTPS and secure and tune HTTPS on the front end anyway, and thus it becomes a core strength of ours as an engineering team, we might as well use it on the back end as well. The other concern we had was the ability to accelerate HTTPS being in general a little bit easier than the ability to accelerate IPsec. That we could do host-level IPsec tunnels reasonably scalably. Router-level IPsec tunnels are at large capacity kind of hard to scale cost-effectively. And so we found that going with HTTPS, besides letting us use building blocks that we were already using and good at anyway, gave us an implementation cost that we could spread across a lot of cheap hardware in a way that was pretty easy to manage. Do we use acceleration offloaders for things like HTTP, SSL? Not directly. The closest thing we use to an SSL accelerator, which arguably should count in this day and age, is we use all of the instructions that Intel and AMD have put into their CPUs over the past several years. The level of throughput you can get for AES and even for RSA and ECDSA from a modern, say, Xeon if you use the latest OpenSSL versions that know how to use SSE, know how to use ASNI, know how to use AVX where available, is on par with what dedicated HTTPS accelerators used to be able to do not too many years ago. And so there's definitely a trade-off there. If you plug in crypto accelerator cards, you can get some nice speed-offs and you can offload from your general purpose CPU. On the other hand, if you use your general purpose CPU, you get to take advantage of Moore's law progress due to competition in that space. You also get the benefit that turns out to be pragmatically kind of useful for us, which is you don't have to have a special server SKU for your servers that do encryption. You can say, well, I'll just have my same general 1U or 2U couple of Xeon rack server that we would use for any other application in the data center, and I'll use a bunch of those for my NGINX proxies. And once you're able to say that, you get some benefits, like if you've got a team in your company that manages your supply chain and is trying to be cost effective about it, one of the things they'll often do is say, we don't want to have special server configurations for every team because it's easier for us to buy one or two common configurations in bulk. And so once you're able to say, well, we'll rely on what the CPU can do as an SSL accelerator, then you get the benefits of being able to take whatever the server was that you buy by the thousands for application use and just use those as a reasonably good, reasonably well accelerated SSL terminator. Question, yes? Yes, it helps to have a recent version of OpenSSL. 1.0.1 added a bunch of Intel contributed code that does assembly language with the right vector registers to make things quite faster. If you're on even newer hardware, OpenSSL 1.0.2 has some AVX enhancements that could give you a better speed up still. And I think for the eventual Skylake Xeons, there will be even more optimizations opened up in OpenSSL. And follow up, yeah?
Thank you so much. Great information. And also, PC will need some like specialized security boxes like F5 this type of how Ajax will be sufficient. How about the appliances?
Right. Okay, so it's the question, how, did we consider appliances as opposed to building our own proxy servers? Yeah. So we thought briefly about appliances, but only very briefly. The economics are much more favorable for running on commodity hardware if you're willing to do more software work. Fortunately, the open source ecosystem nowadays is generally pretty good in terms of making it easy to do the software work. NGINX does what it needs to do, and it works pretty well. IPVS on Linux does what it needs to do for layer 4 load balancing. It needs some better tooling. We're working on that, but works pretty well. And so we found that, and this is in contrast to 10 years ago, or arguably even 5 years ago. Now the software-based open source ecosystem is at the point where you have the option of using commodity hardware for cost effectiveness if you're willing to do some work on the software side. And the work needed on the software side has gotten a little bit easier every year.
Oh, good, this works. Excuse me if this is repetitive, things are running together a bit, but have you looked at HTTP2 and how helpful it will be or not for you?
Yes, so we've looked at Speedy. We use Speedy currently. We're planning to migrate to HTTP2. We're just deciding when. We've found that we still got benefits even on top of using speedier HTTP2. We were already doing things in our desktop client that syncs people's files with their Dropbox to do a lot of connections in parallel for uploads, these sorts of tricks that people used to do on the browser side before Speedy came along, because we, at that point, didn't yet have a Speedy implementation in that client. But we were getting the same effect of parallelizing, getting multiple flows through Slow Start in parallel. So all the results I showed were incremental on top of those that we had already done. Because when you're using Speedy or HTTP2, the good news is you get to push more data through a single TCP connection faster, helps it get through Slow Start more proactively. Bad news is you've still got to get through Slow Start, and you still, for every connection, have the 2 or 3 round trips for TCP and SSL handshake to set it up. And so edge termination takes those optimizations, gives you another level of boost on top of that by saying, well, we can make your handshake a little bit faster. And all of the parts that you're never going to be able to do away with on the average client if you don't support the TCP stack or have the ability to change it in terms of sending more aggressively, why those we can accelerate just by getting the network termination closer to you.
And generally, through these changes, do Dropbox's customers, is their feedback that they perceive you to be slow, fast, or okay?
With one of the first tests that we did, we asked the customers in the enterprise organization that we did the beta with, and their feedback was they perceived it to be fast. They perceived it to be approaching the sensation of speed they got from syncing to a file server in their own office, which was really encouraging to hear, because we, like a lot of other people, are trying to make hosted services work well for the user, and we're all fighting against the speed of light and the distances involved. And realizing that, okay, if we made a bit of a technology investment in getting the proxies together, we could suddenly turn the user experience from okay, where they kind of realize they're shipping bits far away, to pretty good, and it slips their mind that they're talking to servers far, far away. Then we've hopefully helped us, and if this technology is useful, helped other people make hosted services more comfortable to the end user.
Right. Thank you.
So, are you running in a virtualized environment? Virtualization?
Virtualized environment. Yes, in some places we are. We did our initial build out with some servers and Amazon Web Services, and so we were using VMs there. In general, if you grow a really big edge network and you're serving a lot of traffic out of any one location, based on my experience at prior companies, my recommendation is to go to bare metal, because that'll open up the door to a lot of optimizations in the kernel, the NIC, and the TCP stack. But for getting yourself up and running, the bad news is the round trip times on the network dominate everything. The good news is, if you're just starting out and you want to run in a VM, say in a cloud hosting provider, while it won't be as fast as you could make it on bare metal with heavy attention to network tuning, it still is going to be a win, because you'll spend some more CPU cycles, but you'll do it in order to save a lot of expensive network round trips, which are way more expensive than CPU cycles.
Thank you. Can you talk about the networking requirements? What kind of NIC do you use? Do you use SRLV or DPDK, those type of technologies? The networking requirements.
Networking. So networking from edge to internet, we just use BGP with ECMP to connect servers to routers. On the back end, we just rely on a good route back to the origin data center and focus on layer 7, as that's where the bulk of our optimization opportunities are.
Thank you very much.
Thank you. And we're out of time, so thank you all very much. I really appreciate your time.